Thinking back to our example talking about the race earlier, we saw that when we were dealing with the case of the top three, we only ended up with 8 times 7 times 6 possible options to get those, where the idea we used implicitly, not directly, was a thing called a permutation, where for permutations what we're trying to do is select R things from a group of N things where we care about order and we don't have repeats. Order mattering is very, very important with this. Order mattered in that race, so we could think of what we did there as something like, to use this notation, either 8p3, that NPR notation, not meaning National Public Radio, but permutation number, or a different notation that this book doesn't use quite as much, but that I like a little bit better, P8, 3, where in either case, what we would have there is n equals 8 factorial divided by n minus r, so 8 minus 3 factorial, which would end up being 8 factorial over, what's wrong with my 5s? 5 factorial, which, using the ideas we saw in those last examples, that can be pulled out as 8 times 7 times 6 times 5 factorial, or as we saw earlier, just, well, 8 times 7 times 6, which is that value of 336. I'm not going to write here because I think I wrote it before. Hope I did. Well, it's in the notes, so I didn't. And the way we can understand the way that this works, I think I said that too many times there too, is in terms of our counting, in terms of what we're trying to look for here, where n represents the total number of options we have. If you want the total number of options for arrangements where we don't have repeats and we care about order, you have n factorial of them, like we said. But if you only care about the first few of them, the first 3, the first 5, the first however many, what you want to do is you take out the n minus r other ones that don't matter to you, like those other people in the race that finish 4th through last because we don't give them medals for that. So you knock out, in this case, it was the 8 minus 3 or 5 remaining arrangements where you have the factorial for all of those that don't matter. Those divide out and you're left with just the 8 times 7 times 6 or whatever it ends up being in terms of your other n's and r's to get the numbers here. So to help build our understanding of how this works, let's take a couple more quick examples. Suppose you and 11 of your friends have decided to form a club. The group needs to choose 3 officers, a president, a vice president, and a treasurer. In how many ways can these offices be filled? So we have n people, you and n equals 12, people, not n generally. It is you and your 11 friends because you are popular and want to form your club. And you're choosing out of that 11, R equals 3 for president, vice president, and treasurer, where the order in which those selected do matter because, well, some people would rather be treasurer than president, some people would rather be president, vice president, and so on. Who gets picked first, who is the president, does make a difference in terms of their happiness and their role within the group. So, with this number of selections in that group, we have 12 permute 3 total options, which means we're going to take all 12 factorial groupings that can be made and kick out the 12 minus 3 that don't matter to us, the 12 minus 3 factorial in particular, which means taking 12 factorial over 9 factorial, or 12 times 11 times 10 times 9 factorial over 9 factorial, where here, hopefully we can guess that those 9 factorials are going to cancel out. We'll just get 12 times 11 times 10 for a total here of 1,320 possible arrangements of those 3 people from that group of 12. As I said, when we're dealing with permutations and factorials, the numbers tend to grow very quickly. Even just picking 3, you have quite a few. Like I said, the fact that these get big is important and good for, well, most people. Not hackers, but, well, in this case, you're probably happier that life is harder for them. Anyway, let's get one more example here with a different sort of circumstance asking the same kind of question. Find the number of ways of forming 4-digit codes in which no digit is repeated. So, if we're trying to form 4-digit codes, we need to understand here that each of our values comes from one of the 10 digits, 0 through 9. So n here is equal to 10, and we are picking 4 of them, so r is equal to 4. And note here, very importantly, that we are not allowing for repeats, which means that instead of having 10 times 10 times 10 times 10, we're going to have to reduce out our cases. And this kind of hints at the idea that they should call these permutation locks instead of combination locks, but hey, we're not going to worry about that. Where, for this, we have 10 permute 4, and I'm going to go through this formula backwards once just so we can see that it should make sense in that way. That if we don't have repeats, we have 10 options for the first, 9 for the second, 8 for the third, and 7 remaining for the fourth, which we can write in terms of those factorials as 10 factorial over 6 factorial. That is 10 factorial total options, but divide out the remaining 6 factorial, the remaining 6 choices that don't matter, which is to say 10 factorial over 10 minus 4 quantity factorial, as our formula gives us, which, well, to stop holding you all in suspense, ends up being 10 times 9 times 8 times 7 total options. I don't know why I wrote that twice. I said I was going to stop holding you in suspense, which ends up being 5,040, which is a number we've seen before here, as we got in a different sort of example. That's the thing with these factorials, these permutations, and as we'll see later, these combinations, is that because we're dealing with a lot of the same sorts of numbers, coming from the same kinds of places, grammar is just going straight to hell. Well, we're going to see a lot of similar answers. Anyway, that's the idea here for permutations, so let's move on to 11.3 to look at combinations as well.